Chapter 6, Bending, Part B, Parallel Access Theorem, Example 1. Let's review a very interesting example related to moment of inertia, more specifically related to parallel access theorem, and that's a problem that asks us to find the moment of inertia about the x-axis of a semi-solid semicircular area. So if we have a semicircle like what you can see here, and we want to know what the moment of inertia about the a centroid a moment of inertia of a axis like ix, what ix is. So that's a very interesting process. Just follow me in this problem. So far we know ix prime. So this is x prime. This is x, what we are looking for, and this is x naught, which is also called by, for example, I. So this is I x prime, I x prime, I x, and this is I c or equal to I centroid or I x naught. Mhm. So so far we just know I x prime, which is here, which is here. I x prime is a. Do you remember if we had a solid circle? I x, if you call it x prime, I x prime is a force of 1/4 of pi r to the power of 4, and this is r. Mhm. So we have the same problem, but this time the forget about half of the area. So that's just for a half of the area. Again, about the uh, x prime axis. So isn't that similar to our case? And that's a half of 1/4 of pi r to the power of 4. So that's what we know from the geometry of a circle that goes by a, if it was a whole circle, it was going by a force, and if it just goes by a half of the area, it just goes by a half of that. So that's for a semicircle that goes by divided by 2. So that's ix prime for a semicircle. It goes by a half of 1/4 of pi r to the power of 4. That's let's make a bit cleaning. And in that sense, it gives me, if the radius is 20 millimeters, it gives me a, a 1/8 of 20 to power of 4 times pi, and that gives me 2 pi 10 to power of 4 millimeter to the power of 4. And then I just know what my ix prime is. So that's this number. That's ix prime. And if you want to solve the rest of the problem, let's see it based on interesting theorem of parallel access theorem. Yes, it's a two-step solution. So the first one is from what is known to me to the centroid of a semicircle. So do you remember in parallel access to the center, if you're going back home, you're losing. That's a negative. So let's see how that works. So ix naught or I center for centroid, ix naught, which is I for center. It's ix prime. I'm going home from any other axis that's accompanied by a negative. To the center, a negative. From center, a positive. So I need, I need, first of all, I need to know what Ix is. I cannot directly go from ix prime. I'm not allowed to go ix prime directly to ix. You remember, based on parallel access theorem, I need to either go to home from any other access, or then move to any other access. So I have to, if I want to travel between 10 other axes, first I need to go to center from each of them. So then goes to any other axis. As if I want to travel to, again, Urbana Champaign from Edwardsville, and I need to, and in that case, for example, St. Louis is a center. I need to go to uh, St. Louis from Edwardsville, which is my center, then from the center to Urbana-Champaign. So I need to travel back and forth with my center. So in that case, this is a step one. Mhm. From centroid to the other axis is a step two. And this is not permitted. In that case, I'm in the step one, to the center, from ix prime, which is known to me, to the centroid of my semicircle, and from any other axis to home, it's a loss, a negative, and it's ix prime minus ad squared. So let's see how that goes. Let make it a bit or clean here. Yep. So and if you review the do you remember I started bending, chapter 6 bending with two prerequisite, which is the first one is centroid concept, the other is moment of inertia. Then we are moving to the main core of bending moment. So if you review the centroid moment, I am pretty sure I will provide you with the link of calculation of centroid for a semicircle, which is 4r over 3 pi. Mhm. So our radius is 20 millimeters, so that's 4 times 20 over 3 pi. That's our uh, r bar, or d, between x prime and what, x naught. Mhm. So ix naught again is ix prime, which we already calculated, minus a area of a semicircle times d squared, which is just 80 over 3 pi. If you just replace the numeric value, it just gives you, let me clean this. So it just gives you ix prime is, like as I told you, 2 pi times 10 4 from the top, minus a area of semicircle, half of pi r squared, times d squared. D is r bar, and that's 80 over 3 pi. Hmm? If you do the math, it gives you a numeric value for ix naught, or I centroid, of 1.755 to 10 to power of 4 millimeters to the power of 4. Mhm. That was the first step. So far we traveled from any other axis to centroid. Then we want to go to the other cities. So from centroid to the brand new house. So from centroid to any other axis, if you come out from your house, you will get something. So that's a plus. Step two. So step two is from center to x-axis. From is a positive. Do you remember that? From center is a positive in parallel access theorem. I will provide the link to the parallel access theorem video at the end of this video as well for you. So step two is from centroid to brand new house x, and that gives me ix is equal. That's what exactly I'm looking for. So step two, a from center to x-axis. From is again a positive in this sense of parallel access theorem. So then ix is a I centroid plus a d1, and d1 is just a combination of r bar plus 15, which already calculate that's r bar is d. So IC, we already calculated the IC, what IC is, and A is again pi 20 squared over half over 2 and a half of that. And D1 is this time 50 millimeters, which is this distance, plus R bar, which is 80 over 3 pi, all in parentheses to the power of 2. If you do the math, it gives you Ix is a 36.4 10 to 4 millimeter to the power of 4. And that's very interesting that how you can work with parallel access theorem back and forth to get your answer for calculation of moment of inertia between different axes. Thank you.